Hi everyone, I'm Serena. I'm excited to share my senior Keystone project with you guys today. I am a data science major with a stats minor, and I have a strong interest in the intersection between statistics, simulation modeling, and biology and genetics, and this project represents an amalgamation of all those passions combined. So over the past few months, I've built a diffusion model entirely from scratch, combining biology, math, and coding principles, and this goal is to understand how drugs move through the tissue and how that movement can inform personalized medicine by accounting for individual differences in genetics, and anatomy, tissue geometry, and physiology. So before we dive in, I'd like to give a special thank you to my advisor, Dr. Matthew Moore, who has provided me invaluable guidance in navigating through the mathematical and technical weeds of this project. So without further ado, I'll now walk you through how I built and tested this simulation model using MATLAB, which is a tool widely used in scientific computing and biomedical modeling. Now let's start with the big picture. Medications in clinical settings are often prescribed using standard doses, but not all patients are the same. Factors like genetics, age, body type, co-medications affect how the drugs are being distributed and absorbed in the human body. So a one-size-fits-all approach risks underdosing some patients and overdosing others, which is why I built this model to simulate how drug molecules move through the body, encounter tissues, hit barriers, and get absorbed at different rates. So this helps us move towards more personalized and equitable treatment strategies and move beyond the average patient to reflect real human diversity. So drugs don't just appear at their target sites, they have to move through the tissue, travel through it to get there. And they do this through a process called diffusion, which is a process where particles move from high areas of concentration to low areas of concentration. But the body isn't just an empty space, there's stuff in it. So as molecules move, they hit barriers like membranes or get absorbed by organs. And these barriers behave differently depending on a person's biology, tissue geometry, health status, whatever genetic factor, which is exactly what my model simulates. So I represent the tissue as a 2D grid. Each square is a small patch of tissue. And to simulate drug entry, I initialize boundary cells with high concentrations, and then the expected model behavior is that particles then diffuse into neighboring cells or more interior cells with lower concentrations. And you'll see what I mean in a moment with more advanced, complex grid setups. But for now, just focus on this 2x2 simple grid setup. So in this example, I don't know if I can play the simulation, actually. Okay, 2 cells start with 30 particles and 2 start with 0, totaling 60 particles in total. And over time, they balance at 15 particles each, which shows both mass conservation and realistic diffusion behavior. And the simulation updates the entire grid in parallel at once, and it's powered by linear algebra, matrix math, and something called random walk theory, which I'll get into a moment. But essentially, after n time steps, they converge into equilibrium, roughly the same amount of particles per cell. So at the heart of the model is a powerful connection between diffusion and something called random walks. Think of diffusion like dropping ink into the water. The particles naturally spread from crowded regions to emptier ones. And what's fascinating is that we can simulate this spreading of drug molecules through the tissue using random walks. So each particle takes small random steps, left or right in one dimension, or left, right, up, and down into their neighboring cells in 2 dimensions. So even though each step is random, the overall pattern that emerges for this particle behavior is predictable and actually forms a smooth bell curve. In math, we call it a Gaussian distribution, which is exactly what we see in real diffusion. And this simple stepping logic captures complex drug behavior and becomes even more realistic when we add the fun stuff, like the biological barriers and mathematical constraints. So how do the particles know when and where to move? Well, it's based on a very few simple rules. First, every cell that contains particles must move 1 particle per time step. No skipping is allowed. The only randomness is in which the direction moves, but that randomness is guided by deterministic probabilities, meaning the likelihood of moving in a certain direction is based on the concentration of the current concentration of the neighboring cells. And a particle is more likely to move towards emptier neighboring cells and less likely to move towards full ones. But the most important principle is the mass of particles, and they have to be conserved, meaning the total number of particles in the system cannot change unless we simulate like external forces, such as artificially injecting particles through IV to simulate drug entry or some sort of drug loss process. No particles are created or destroyed. So to kind of further illustrate how the particles choose which neighbor to go to per time iteration, pretend you're a particle in the center cell and your neighbors are the 4 highlighted boxes. So Each particle in the cell looks at its four neighbors, up, down, left, and right, and you prefer to move into the emptiest one. The less crowded a neighbor is, the more likely you want to move there as a particle. And we convert these preferences into something called movement probabilities, and then build a cumulative list from them, each value representing how likely the particle is to move in a given direction. And then we roll a virtual die, pick a random number from 0 to 1, and the particle moves in the direction whose range the number falls into. In other words, the particle follows the path determined by the probabilities in that cumulative list. So once a direction is chosen, the particle leaves its current cell and enters the neighboring one. And this happens across the entire grid at once in parallel, which creates a smooth, realistic diffusion pattern over time. Now let's walk through how particles enter and exit the system. This is where something called excretion and injection come in. So the simulation has three main zones: interior cells, boundary cells, and padded cells. Interior cells represent the tissue like an organ or bloodstream. This is where drug is accumulated or acting on. Boundary cells act like the edges of the tissue, similar to skin or vessel walls, and it controls what exits and enters the system. Padded cells surround the system and simulate external drug sources, like an IV or inhaled air, and those cells don't store particles. They always act like always-on portals that constantly deliver particles into the boundary at a fixed rate. And I can choose whatever fixed rate this may be. It's totally adaptable in my model. And we can control how fast the drug is delivered by adjusting how many particles each padded cell injects per time step. And that simulates different delivery rates, like a slow IV drip or quick release spray. And we can also control how the likelihood a particle enters from the padded cell and exits the padded cell, which simulates drug entry processes like IV, spray, or cream, or drug loss through sweat, breath, or metabolism. So on the right, boundary cells are full and interior cells are empty. And by step 500 in the bottom, you can see that the particles diffuse inward, which forms an even distribution across the tissue. And this is the animation that displays that. And you can see over time that it sort of converges into a nice orangey reddish color, showing that there is roughly approximately the same amount of particles per cell, which satisfies mass conservation. So here we apply the same model setup and logic from the simple grid to a more complex tissue geometry, one that more closely resembles like an organ cross-section or targeted drug delivery site, one that is more reflective of real biological structures. And you can see that it reflects a curved, irregular surface, but the underlying rules are the same. The padded cells inject particles, boundary cells regulate entry, and interior cells accumulate the drug over time. And the particles still diffuse inward, and the shape influences how they spread of the tissue geometry, which mimics real organs. And let's see if I can play this. So now, as we let the simulation run, you'll notice that interior cells start to hold a similar concentration, showing that the equilibrium is achieved regardless of the tissue shape. And you'll notice the padded region stays black throughout, remains at 0, which acts as a virtual syringe that injects particles into the boundary but never stores or accumulates them. So I'm not going to play this for longer because you can kind of see the behavior, but so to make the model more biologically meaningful, I scaled it up to an 1,000 by 1,000 matrix, a rough approximation of the human body. And that's just 1 million cells representing the tissue across the entire grid. But this isn't just for visual effect. Large grids allow realistic simulations of how the drugs diffuse through full body structures, including limbs or organs. And at this scale, we can explore how drug delivery changes across body types, and it'll help us better model personalized treatment pathways. Now, this simulation helps us understand how the drugs move through the body, not just in theory, but across space and time. So modeling diffusion over time through the tissue, we can begin tailoring drug delivery to individual patients, adjusting dose, timing, and target location, which is especially useful in lab-grown tissue or simple organ systems where passive diffusion is the main driver. So it's great for controlled environments. So while this is just a starting point, it lays the foundation for more complex clinical models and smarter, more personalized treatment strategies. But right now, this simulation has limitations of its own, and real life is more complicated because in the body, drug molecules can get broken down, metabolized, be pushed across barriers through active transport, or interact with cells in ways this model doesn't yet show. So in the future, I hope to model as many different types of tissue geometries as possible, realistic ones, including special cases such as post-op surgical cases or amputations, accounting for differences in cell density or thicknesses, including factors for blood coagulation, and even how the slightest bit of arm movement can affect how particles diffuse in the body, and circulation, and your circadian rhythm alters not circadian rhythm, but the circulation patterns in your arm are adjusted and need to be adjusted for. So in the future, I hope to support personalized medicine with this model and add more biological constraints and enable drug delivery models that adapt to each person's biology. Thank you. Any questions, Cam?
Amazing presentation. What was the hardest part of making your model? Because that looks intense.
Pretty much, I kept failing, the mass conservation principle. So at some points, the whole grid would just either totally be blacked out, meaning they have 0 particles, and they would all leave randomly the whole entire grid. So that was frustrating. Sometimes some particles would be way too high in concentration, others would be way too low in the entire grid. So that wasn't making sense at all. And then I had problems reading the TXT file that allowed me to make this human body scale simulation on MATLAB, but that was a pretty rudimentary error on my end.
Congratulations, amazing project.
Thank you.
So I was curious about for your next steps, because you want to go into more realistic models. Are you thinking about 3D models? And if so, how would you go about that?
Yeah, that's a great question. And if I had the time and computational power and resources to do that, I surely would. But, and instead of an n by n grid, I would have to do an n by n by n grid. But it would be a great way to map, the stochastic behavior of particles in a more realistic way, and I would be able to really map particle motion across cells in a 3D way that I can't really quite capture in this 2D grid setup. So yeah, it would be interesting to see that. And I think capturing random motion of particles would be a great way to do, would be fantastic on a 3D grid setup. Unfortunately, I don't have time or computational resources, so yeah.
Thank you.
All right, thank you, Serena.
Thank you.